Go. I don't know if dogs actually eat paper. This is electromotive force. This is the last section of your circuit notes. So here we go. We know that a battery, which is this bunch of cells, is a source of potential difference. What's another word for potential difference?
Voltage.
Voltage. Good. In our analogy with the trucks, what is the voltage?
Amount of energy per truck.
Good. Perfect. Thank you, Serena. So our trucks go around the circuit, and you have the amount of energy per truck is voltage. And the voltage, if it's, just underline this part, between the terminals. If it's between the terminals of a cell, it is also called electromotive force.
Electromotive force.
Yeah. Okay. So we'll write that here. Electromotive
Oh, it's electromotive. Do you need a dash?
Force. And we say EMF. Yeah, it's usually you see it with a dash. You don't see it written out very often though, I have to say.
Too long, right?
Electromotive force was the term given to the push of the trucks around the circuit, and that was from Michael Faraday. Did I tell you the story of him with the fingers in school?
What finger? No?
Hannah remembers. Why don't you remember?
No, we talked about electrocuting someone, not fingers getting chopped off.
Oh, that was Tesla. Who here remembers the Michael Faraday story? He went to school and the finger. Yeah. See, I told
Oh, wait, let me think. Oh, wait, no. Wait.
you. Okay, so it's called electromotive force, which is confusing.
I remember.
Because this is not actually a force. It's a voltage. But it's kind of just a leftover from Faraday. He just called it electromotive force and we just kind of kept it. But there's a subtle difference between EMF and voltage across the terminals, and we'll go through that now. So if you have a car battery, it has an EMF. Anybody know the voltage of a car battery?
No.
Thank you, Hawk. 12 volts.
No, that's not a lot.
No, it's not too much actually. It's pretty low. Tesla would like to make it 48, but we'll see if that happens. Anybody know a lithium-ion battery voltage?
3.7.
That's good.
Wow.
3.7
Random things. But yeah, actually.
volts. And what's the voltage of the little batteries that you guys were using?
1.5.
Yeah, 1.5. That's good, isn't it?
Why
So-
do people have memory?
A regular cell would be 1.5 volts. Now that's the EMF of the battery. It's kind of like the best that the battery can do.
Oh.
So here's a question. What happens to that energy on the trucks as it goes around the circuit? What happens to the energy in the trucks?
Less like every time it goes
It loses voltage, so it drops voltage as it goes around the circuit. What happens to that energy? Does it disappear?
Just don't transform it.
Yeah, it gets transformed into light or sound or heat or whatever you want. That's because all the things around the circuit have a resistance. Yes?
Yeah.
So here's a question. Ronia, does a battery itself have a resistance? Who thinks no?
I have no clue.
Who thinks yes?
I'm not gonna raise my hand.
Who thinks, I don't know.
That's me. But
Who thinks I'm too tired to raise my hand?
but if you're too
Who just came in late so they can't raise their hand because they're too late?
Like,
That's Lewis.
you're too lazy to raise your
I'm glad
hand.
you're here,
Raise
Lewis.
your hand.
A battery does have a resistance. It's small, but there is a resistance there. So just to push the electrons through the cell takes a little bit of energy. So you always kind of, when you measure the voltage gain across the cell, it's always like a little bit less than like the perfect total voltage that the battery could have. It's kind of like air resistance, you know, like you measure something falling and you get 9.8, but with the air, it's always a little bit less, right? This is the same with electricity. There's always a little bit of resistance in the battery. Okay. So we always say it's less than EMF.
I like that pen. The pen was nice.
You like this pen?
It just seems like,
It's a nice color, isn't it?
yeah.
And this is due to the fact that every battery, let's see what this one looks like, has internal resistance. Oh, that's not good. That's not a good color. How about this one? No, I'm gonna make it dark so you can see it.
You can trace your own writing.
Yeah.
I don't think I can trace my own writing.
Okay, tell me, what is internal resistance? What does that mean?
Resisting the battery.
Yeah, it's just the resistance the battery has. So some of the energy that the electrons have, that the trucks have, is going to get turned into heat as it goes through a battery. That's why a battery will warm up as it's getting used. You know how your phone gets hot sometimes?
Yeah.
Yeah, it's because of this. And so because of this, now we have to write it twice, sorry. Because of this internal resistance,
My writing is
because of this internal resistance, the terminal voltage is always, what would you think this is going to be?
nice.
Good. Less than, whoa,
What's this box looking like?
less than EMF. It's a formula box.
Oh, I'll just ignore it.
I'm gonna say,
What if I'll move it down because it seems better?
so the internal resistance makes it so that the terminal voltage is less than the total EMF. And I'm gonna go back to my nice pretty pen.
Is that a T? Oh.
So V terminal is equal to the EMF, which is kind of the theoretical total voltage of the
Is
cell.
that the sample?
Yeah, minus
I can't draw.
IR.
It looks like two E stacks on each other.
Wait,
I
so
won't.
is that like a spring looking thing? EMF?
Yeah, this is an epsilon, that's a Greek letter.
Then what's IR?
You tell me what I is.
Amps?
Yes, good, current in amps. Yes,
What's
Melanie.
R then?
What is V terminal?
Very good question. So V terminal, we should write this out actually. So the V terminal is the voltage measured across the cell. Or I'll say battery, I guess, because we're using the term battery. So when you put the voltmeter across the battery and you get the voltage of the battery, that's the terminal voltage. What do you think? Are you ever going to be able to measure the EMF?
No, I don't know.
It's theoretical. You can calculate it, if you change the resistance in the circuit, you make a little graph and you can go, it goes up to here, and it would be perfect if the internal resistance was 0. But you can never actually measure it because the cell always has some kind of little bit of resistance. Yes, Sophia?
That's internal resistance, right?
This is internal resistance, yeah.
But how will we know that?
So the epsilon, this is Greek letter epsilon, and that is the EMF. And I'm just going to put in brackets here just to make it clear. This is like the theoretical perfect voltage. And I is just current. Is the current going to be different through the battery than it is through the rest of the circuit? Or will it be the same? Yeah, it's going to be the same. So the I is current. And the little r is internal resistance. Which is the resistance inside the battery.
I times R?
Yeah. So the I times the little r is kind of like, it's the voltage drop, right? Because V equals IR. So it's just like any other resistance in the circuit. You do current times the resistance and you get the voltage drop. And it's the same with the battery.
Just was where IR knows the battery is not connected to a circuit.
These things that I put here is this part.
Okay.
Well, I guess we could write that out. So this is the voltage drop inside the battery. Put that one in a little box. And if the battery is not connected to the circuit, then
Where did you put that for? Oh,
then the V term equals the EMF. Sorry, ugly. So the only time the EMF equals the terminal voltage is when there's nothing happening, there's no movement. And you can't measure it because nothing's moving. Turn to the person beside you and tell them two things. Tell them what terminal voltage is and tell them what EMF is.
Measure. Terminal.
Samuel, tell Dylan.
Batteries, when not also slowly lose batteries not also
Emily, I'm filming this so you can get the
they still react.
earlier stuff later. It's still going on, but it's not too bad. Okay, who can tell me what's terminal voltage? Serena Osque.
voltage measured across the battery.
Good, so that's the voltage that you measure. And Ilya, what is EMF? Electromotive force, yeah.
Perfect.
So what does that mean?
I mean, perfect.
Hawk, what does it mean?
Theoretical voltage of the battery.
Yeah, it's the theoretical full voltage of the battery. What, to have the measured voltage be equal to the EMF, what would the internal resistance of the battery have to be?
0.
Good, 0. Is that ever going to happen in real life? Not that we know of, unless we can make a superconducting battery or something like that, which we haven't done yet. Okay, flip this over to the next page.
Consider this one diagram. I don't see
Okay, so we're gonna just draw out this
The battery
diagram.
goes dead is because the chemicals are gone. There's no more. It all reacted. Why would I not?
That's like more than I've made this year in my life.
So we're gonna draw this circuit the same as all the other ones we've done. Except this time we're gonna add a teeny little resistor in front of the cell. And then we're gonna draw a dotted line around it like this. Bless you. So inside this dotted line is the cell. Cell or battery. So what's the little resistor inside the dotted box?
The internal resistance.
Yeah, that's the internal resistance. So you can kind of just treat it like another resistor in the circuit. It just happens to be attached to the battery.
Okay.
Oh, and this stuff is like external resistance is R. Internal resistance is little r. And EMF is the squiggly epsilon.
This is double E.
So this one you would say is R, big R, and this one is little r. So when a battery goes dead, it's because the internal voltage drop is equal to the voltage drop outside the cell. We can say that.
How would there be an external voltage drop if it's dead?
Well, there won't be because it just isn't doing anything.
So it already dropped.
Okay, read this little example and try to do it on your own.
If I'm getting the calculator because I can't do mental math. Even if it's 12 plus 2, I can't do it.
See if you can do it yourself. Use this formula.
V equals IR.
Bless you. Are we going to be able to use this formula as it is?
Probably.
Isn't it minus IR?
Oh, sorry. I put it equals there. Thanks, Serena.
Yeah, why not?
Minus. Yeah, I think we can use it as it is. So the 12 is the EMF, so that's what it would be if it was perfect, but it's also going to have a voltage drop of 3 amps times 0.22 ohms. So that's going to be 0.66, and 12 minus 0.66 is 11.34 or something like that.
Yeah.
Did anyone do it? Let's see. Oh, these calculators that don't work.
I think I am Zell. Think people love naming things Zell, don't you think so? There's like,
It is 11.34.
there's like so many things named Zell.
What's the unit? Is it just
At least I know.
You tell me. What do you think? Yeah, just volts.
A cell on your body.
Who got 11.34 volts?
Yeah.
Who didn't do it yet? You guys are all like lazy today. What's going on? Hi, Melody.
How can you tell the difference, like in the question, how can you tell the difference between the VT and the EMF?
Yeah, that's a good question. If it just says it's a 12 volt battery, that's EMF, not terminal. If it says that you measured 12 volts around the battery, that's V terminal. And if you're wondering, you can ask me. I'll tell you which is which. Okay. Okay, this is a little bit of a weird one, but just because you guys all have cell phones and you're always charging your phone, if you're charging a battery, which way is the current moving through the battery? Yeah, it's going backwards, right? So instead of it being the EMF minus IR, you actually have to charge the EMF plus the IR. Because as you charge it, you're losing some energy in the battery as you charge. So you have to actually you have to charge it with more voltage than you would measure it going the opposite way. So it's VT equals E plus IR. Now, this is kind of like, it depends whether you're mathy or real worldy. If you're real worldy, you're gonna use this formula, but if you're mathy, you just use the same formula, but what's the I going to be?
Negative.
Yeah, that's right. Thank you, Sophia.
Oh.
So because it's going kind of against the circuit, you make it negative and then you add it anyways.
Only when charging.
Yeah.
When charging.
Yeah. Oh, sorry. Can't see that. So last example, let's do this and then we'll do something fun. Kind of fun.
What's an alternator?
An alternator is the thing in your car. It's like it's funny because we use gasoline cars, right? But everything we use in the car uses electricity.
Yeah.
So we need to charge the battery somehow. So when your engine spins, it spins this little motor thing that creates electricity to charge the battery to run all the stuff in your car.
So when you're using the gas, you're also generating electricity.
That is correct.
Oh.
Yeah, and so that's why, like, if you're driving on a summer day and you turn the air conditioner on, your gas consumption will go up.
Because you need more of it.
Yeah, that's right. Because it'll be harder to turn the alternator. You need more gas to turn the alternator, to charge the battery, to run your air conditioning,
Oh.
and then you get less miles.
Oh.
If you have an electric car, it's a little bit different, but.
I don't have one.
Okay, so let's do this one. So what's the EMF in this one?
You mean 12?
Yeah. The EMF in this example is 12 volts. And this time, because we're charging, we're going to add it. Oh, so this VT is going to be 15. I should have done this backwards. I'm going to start this again. If we have VT equals EMF plus IR, and we're looking for R, how do we solve this for R?
Are we doing I or R? What's the current with that?
The current, oh, sorry. We already know R, so we need I, yeah, sorry.
That is subtract.
Thank you, String. So we need this one. How are we going to solve for that big I?
Divided by R. Okay.
We can do VT minus the EMF, and then we're going to divide it by the little r, and that should give us our current. So our charger is providing 15, and that's minus 12, and then we're going to divide it by the 1.3 ohms. And that's 3 divided by 1.3, which is 2 point something.
2.3, and then that's what I got. It's wrong.
2.3?
That's what I got.
And what would that unit be?
Amps.
Amps. Yeah, sorry.
Do we have to put a negative or we can ignore it?
That's a good question. If you're doing it this way, I would just keep it the magnitude of it.
Yeah.
If you're doing it the other way, if you're starting with this formula, then I would make the current negative.
Okay.
It's gonna come out negative anyways. And then you just, you know it's going backwards. That depends how your brain works.
Oh, that's one.
Okay, that's it, you did it.
Wow.
Yay. You are finished. Electric circuits. I'm gonna stop this and I'll post it later so people can see it.